Does everyone recognize Mr. Ed? Are y'all old enough to remember Mr. Ed? Yeah, Mr. Ed was a talking horse. It was incredible. And they made him talk by putting peanut butter in his mouth, and then just for the whole show he was trying to get it out of his mouth. It's waterboarding for horses is what it is, and it would never be allowed. So anyway, this is the start of the show.
Hello, I'm Mr. Ed.
A horse is a horse, of course, of course. Anyway, we're going to find that there's one equation that gives us the voltage difference between 2 points in a very, very simple fashion, as long as the electric field in that region is uniform. We call it the Ed equation for reasons that will become apparent. Let's take that second kick at the can. What we really care about is the change in the electric potential energy as something goes from A to B. And we find that by taking the voltage from A to B and scaling it by the test charge that we're actually moving from A to B. In that sense, this voltage is a rate. When I say there's 120 volts from A to B, what I say is that's how much I would store, how much electric potential energy I would store if I took 1 coulomb from A to B. Well, if I take 2 coulombs, I just store twice as much energy. 5 coulombs, 5 times as much energy. Okay? Now, if I remember from 205, external Verk is what changes total energy. And in these problems, when we say total energy, we mean kinetic energy and electric potential energy. We are typically dealing with things like protons and electrons that have such a small mass that we don't really care about the change in gravitational energy. It's negligible. And so if I grab that object and move it in such a way that it starts at rest and ends at rest, then there's no change in kinetic energy. And that gives us a conceptually simple way of measuring how much energy we stored in the system. Well, how much Verk did I do to cock the spring? Okay? Well, let me see if I can make that visual. There's a younger Greg Francis. If we put a bowling ball over his head, he is not, I repeat, he is not afraid. Okay? That bowling ball doesn't have the capacity to do any damage to Greg's head. And that's because it has a low gravitational potential energy. Energy is the capacity to do damage. I'm not afraid. Okay? Likewise, if I put a positive charge right here next to this negative plate, that's where it wants to be. That's its happy place. It doesn't want to be near that positive plate. It wants to be here at the bottom of the cliff. Okay? In that case, I would say it is at a low electric potential energy. Now, in order to find out how much energy that I store, I just calculate how much Verk, an external agent, the hand, has to do to take the bowling ball somewhere else, or to take the charge somewhere else. And if I lift that bowling ball, the hand is pushing in the same direction that the bowling ball is going. The hand is doing positive Verk. If we do it in such a way that we don't change the kinetic energy, that Verk, that positive Verk, is giving me a positive change in electric potential energy. I'm sorry, in this case it would be gravitational energy, right? Okay, now, what that positive change means is I move to a region of higher gravitational potential energy. When the change in your bank account is positive, you do the happy dance. That's a positive change. It got bigger, it got fuller, okay, the bank account. Now, in the same way, by pushing this positive charge against the field, just like I was pushing this bowling ball against the gravitational field, I'm pushing this positive charge against the electric field. I'm doing positive error. It doesn't want to go there. I've got to push in the same direction it's going. And by doing that positive error, I'm storing energy. In this case, I'm cocking an electric spring. In this case, I'm cocking a gravitational spring. But either way, I'm cocking a spring. I'm storing energy. Okay? The change in electric potential energy would be positive. Now, what happens when I let them go? When I just let them go, suddenly, I find I've got kinetic energy. Okay? The bowling ball has the capacity to do damage to Greg's head. The positive charge now has capacity to do damage to this plate. They have kinetic energy. Now, if I go back to this original equation here, clearly it's not the change in kinetic energy that's zero now. What's zero, in this case, is the bearing. The hand just let him go. Did not do any bearing. Just let it go. And now we see that whatever change I have in kinetic energy has to be accompanied by an equal but opposite change in potential energy. Okay, I can rewrite this as the change in kinetic energy is equal to the change, in this case, electric potential energy, but I've got to have a minus sign there. If this is a plus 6, that has to be a minus 6, so that when I add them together, I get 0. And if this is minus 6, and I multiply a minus 6 by a minus, I get a plus 6. That's what that's saying. Now, folks, where does the kinetic energy come from? When you go to sleep at night, right before you go to sleep, I don't care what you have been thinking about, from now on I want you to think about this picture here. Throughout the spring break, whatever beach you're on, this is what goes through your mind before you go to bed. Okay? What this tells me is that in order for the kinetic energy bucket to fill, the potential energy bucket has to drain. It's a zero-sum game. In order for me to get an extra 6 joules here, I got to lose 6 joules there. Now, folks, when we talk about kinetic energy is 1/2 mv squared. I know what it is initially, I know what it is at the end of the motion. I just take final minus initial. But when I'm talking about the change in electric potential energy, I don't have a 0 that's set for electric potential energy. All I ever care about is how big the change is. Okay? Just like we never care where the 0 of height is, we could call it sea level, we could call it Main Street Bozeman. It doesn't matter. Likewise, the change in voltage, whether we go from 500 volts to 600 volts, or whether we go from 800 volts to 900 volts. Either way, I get exactly the same physics. So when we're talking about the change in electric potential energy, we leave it in this form. Okay? Now, the other thing that I would like you to focus on during break, when you're not on a beach, is the fact that I have the same relationship with the electric field as I have with electric voltage. They are both rates. I have this equation relating the force that I care about to the electric field as just a gimmick. Okay? I have this relationship between the electric potential energy that I care about and this voltage thing that's just a gimmick. Okay? If I set the test charge equal to 1, then I see what this gimmick is. The electric field is the electric force. if the charge we're pushing on is 1 coulomb. Okay? It's like going into a gas station where they have a big sign that says, price of gas, $2 per gallon. Any grade, $2 per gallon. And you go in and you say, hey, how much would it cost to get a gallon? Should you feel stupid? Yes, there's a sign. $2 per gallon. And that's what this is saying, is when you're getting 1 unit of charge moved, the electric field is the electric force. That's how I understand what the electric field is. Okay? If you want 2 gallons, it's $4. 3 gallons, it's $6. Do you see a pattern? Okay. The same thing is true with voltage. When I say that the voltage is 120 volts, what that means is that whenever I move 1 coulomb of charge from A to B, I'm storing 120 joules. A volt is a joule per coulomb. I'm storing 120 joules. If I move 2 coulombs, twice that much. Okay? It's a rate. It's a rate. These are the things that we really care about. This is how we get them. Check that your neighbor's on the bus. If not, just slap them till they are. Do what you got to do. Okay. Let's look at problem 3 that you voted off the island. I'll just point out that this problem, problem 3, is the voltage problem. I mean, there's only one, and we dress it up in different ways. But this is it. And you're bound to see it on the midterm, okay? This very problem. Now, what we find in this problem is that there's a location that we call A and a location that we call B. And we have a proton and when that proton gets to A, it has a velocity of 1 times 10 to the 5th meters per second. And when that same proton gets to B, it's going 3 times faster. And we're told that the voltage at A is equal to 1,000 volts. And we want to know what the voltage at B is. Now, folks, I wish I had a different story to tell. But one of the most common mistakes that people make on that second exam is mixing up their V's. I mean, you can see that voltage starts with V and velocity starts with V. It's not my fault. They've been using these letters forever. It's not my fault. But a lot of people just start plugging V's into any formula and they get garbage. Now what I'm going to try to do throughout my lectures is I'm going to try to make these voltage V's capital and boxy. Okay? And I'm going to try to make these velocity V's just as frilly as my shirt. I'm just going to make them French. Okay? I teach a seminar for the graduate students when they first come here on teaching. And I had a graduate student from France, and whenever they have to each do a lesson, and then their peers grade them. And when this French graduate student did his presentation, he had some evaluations from some of the female graduates. Says, "Oh, he's so dreamy." His accent is just so heavenly. So anyway, I sat down to talk to him about his teaching, and I showed him these comments, and he said, "Oh, I'm glad they feel that way. It was certainly not working for me in Paris." Okay, that's not going to be on the exam. Okay, but we'll make these as French as we can. Okay? Now, here's how you solve this problem, which is all the problems. You start with the Grand-High-Werk energy equation. However, in 99% of the problems, the Werk done by the external agent, the hand, is 0. And 100% of the problems, where the thing that's moving from A to B is a proton or an electron, you're guaranteed the Werk is 0. Why? Because you can't grab a proton. Okay? You can't grab an electron. And so that's going to be 0. And so this is where you're going to actually start. That equation is the starting point for 99% of your problems. Now, the only case where that's not the case is when you're dealing with something heavy like a rubber ball that's been charged to 3 coulombs. Okay? But if you've got a proton or an electron, that's the starting point. And when you see that equation, you should see this picture. Okay? It's a zero-sum game. In order to get this bucket to fill, I got to get this bucket to empty. And that's what that minus sign is telling me. I got the same size change, but one change is positive and one change is negative. They have opposite sign. At this point, it's just plug and chug. When I have kinetic energy, it's just final minus initial. Well, in this problem, I'm going from A to B. That means my kinetic energy is going to be final minus initial. My electric potential energy, I just replace with the test charge times the change in voltage. Okay, that's the rate. And I've still got that minus sign. In these problems, minus signs are everything. If you think you can throw away minus signs like we did with the electric force problems, you're going to get way messed up. Every single minus sign is important. And in some cases, you'll have 3 minus signs in your problem. Okay, you got to keep track of each one of them. Now, just like in 205, when we did energy problems, things very quickly became algebra. The same thing is true here. You write down this formula, it's the same formula every time, and you plug in. And at that point, you're just solving for the unknown. I know what the mass of the proton is. It's 1.67 times 10 to the minus 27 kilograms. I know what the speed at B is. It's given. I know what the speed at A is. It's given. I know what the charge of the proton is. It's the elementary charge. Going to be on the front page of the exam.
Can you cancel 1/2 in there?
Can I do what?
Because they're the same on both sides, can you cancel 1/2 M?
No, because I don't have a 1/2 M over here.
I meant, well, you're subtracting one from the other, you're subtracting the same thing.
I could write it as 1/2 M VB squared minus VA squared. Oops, that's curly. But I still have to keep the 1/2 M there because I don't have it on the right-hand side of the equal sign. Okay, at this point I only have one unknown. It's this voltage difference. When I solve for that, I get a negative. That negative sign is critical, 417 volts. Now, if the voltage at A is 1,000, and I've got a change as I go from A to B of negative 417, my voltage at B had better be smaller by 417. And the answer is 583 volts. Check that your neighbor got that answer for problem 3.
Well, we went and found the kinetic energy. We found the kinetic energy Yeah, but why can't you find the change in kinetic energy? Because like you said, if the kinetic energy goes down, the potential energy will whichever bucket has to fill.
No, the change from A to B. Protons want to race this way and speed up as they go. They speed up downhill. A change in voltage that's negative. Think of that voltage as an elevation. Okay? Now if we have an electron, on the other hand, the electric field points from positive plate to the negative plate. That's independent of the electron. That's parallel to those field lines. But the electron feels a force, that's the thing that's real, that is opposite the electric field. If this electric field is the force that I would have if I put a 1 coulomb there, a plus 1 coulomb, if I put a negative charge there, it's going to be pushed the other way. Now remember, the voltage is always higher near the positive plate. The electric field always points from the high voltage to the low voltage. Okay? And so that means that a negative charge, like an electron, wants to go towards that positive plate. It wants to go uphill. And this causes some confusion. In gravity, everything falls down. Everything falls from the top of the cliff to the bottom of the cliff. Well, most everything. My kids were selling fireworks one year, and we were in a bad location. So as a father, I felt I had to do something. I went out and spent $600 on this huge black cat blimp. I spent a whole lot more money on helium to fill it up, and we would float this over their stand. And every night we would park it on top of the stand. My redheaded son, who's just finishing his orthodontics program, he's a good sleeper. He's an excellent sleeper. He was asleep in the stand. At 2 in the morning, some people came and cut it loose. And whenever you own something that falls up, you don't have it for long. Anyway, most things fall down. Okay? Now, we can make everything fall down if we redefine what we mean by down. And that's what physicists do. We like everything to always work the same way. If I look at the gravitational case, the gravitational field always points from high elevation to low elevation. I only have one kind of mass, positive, and it speeds up in the direction of that gravitational field. Okay? Now, if I look at the change in kinetic energy while it's speeding up, that's positive. That's what speeding up means. Your kinetic energy bucket's getting fuller. That has to come at some price. That kinetic energy comes from a decrease in potential energy. The potential energy bucket has to empty. Now, we also know that the height or elevation must decrease as something speeds up in the gravitational case. If we look at the electric case, the electric field always points from a region of high voltage to a region of low voltage. And if I have a positive charge, that's going to speed up in the same direction as that electric field. Now, as it speeds up, the kinetic energy is positive. That's what it means to speed up. That energy has to come from potential energy, so the bucket of potential energy has to empty. Its change is negative. And the voltage is going from 250 to 150. If that was your bank account, you'd call that a negative change. So far, so good. Okay? Typically, we call down a decrease in elevation. And in electricity problems, we associate elevation with voltage. The wrinkle comes when we look at negative charges. They speed up in the opposite direction of the E field. Okay? But they still speed up. And that's a change in kinetic energy that's positive. That increase in kinetic energy has to come from a decrease in potential energy. But the voltage now is going from 150 to 250. If that were your bank account, you'd call that a positive change. Now, if we call this down and this down, then we have to deal with charges that go up. What physicists do is they redefine down. They say everything falls to a condition of lower potential energy. Okay? Everything seeks a lower potential energy. And in that case, everything falls down. You just have to be careful how you define down. Now those those voltages there could be caused by plates, where this is a negative plate near the low voltage region and a positive plate near the high voltage region. This positive charge is racing towards the negative plate. This negative charge is racing towards the positive plate. And that's what's causing the increase in speed. Check that your neighbor's on the bus. Do another buddy check. See if they know what down means. Voltage difference is how much air I have to do. And if I wanted to break one from the negative plate to the positive plate, it doesn't want to go that way. It's going to go positive air. Yeah, you can try to hold fire, but the voltage is much higher than the charge of the voltage is very low. The voltage difference Okay, folks, the reason that I've got a higher voltage near the positive plate is voltage. Think about what voltage is. It's how much Varric I have to do on a +1 coulomb. Well, if I had a +1 coulomb and I wanted to get it up there, would it want to go up there? No, it doesn't want to be near that positive plate. I'm going to have to fight to get it up there. I'm going to have to really push hard in that direction while it moves that direction. Is that positive Varric or negative Varric? Positive Varric. The Varric is what the change in voltage is. If the Varric is positive, the change in voltage is positive. That means the voltage is getting bigger as I go towards a positive plate. Does that make sense? Nope. Okay, let's look at this problem that you turned in. You have point A. Let's reset the problem. You have point A that has a voltage of 750 volts. And B has a voltage of 950 volts. And we have an electron and it's going at some velocity at A, French. And the question is, when it gets to B, will it be going faster, slower, or the same speed? Tell me with your clicker. Okay? Good, 98 of you got it right. Now, here's the reasoning. The change in voltage, as I go from A to B, well, 750 up to 950, that's a positive change. That's a change of plus 200. So that's positive. What I really care about is this energy bucket, the potential energy bucket. And that potential energy bucket is the voltage change times the test charge. Well, if this is a plus 200 volts, and this is a negative 1.6 times 10 to the minus 19 coulombs, well, a positive times a negative gives me a negative. That means that the electric potential energy bucket, the one I really care about, is decreasing, emptying. It's a zero-sum game. When one bucket empties, the other one fills. And if you're increasing your kinetic energy, you're speeding up. Okay? You're going faster. Does that make sense? Okay. Now, what I'm going to do is I'm going to quickly derive for you the ED equation. It's very simple. Don't worry about derivations hurting anything. Let's say that the voltage difference from A to B is some value V naught, 300 volts. What that means is that if I take a 1 coulomb charge and push it from rest to rest at B, from A to B, I as the external agent have to do 300 joules of air. Okay? That's what voltage means. Now what if instead of that electric field, I was fighting a field that was twice as strong? Well, if I could push that 1 coulomb across with one hand, now I'm fighting a field twice as strong. I got to push twice as hard. How much Vert do I have to do? Twice as much. Okay? So twice the field, twice the voltage. Hold that thought. What if I go back to the original field, but I move point B so that I only have to push half as far? I still have to push as hard as I was in the original case, but I only push half the distance. Vert is force times the distance. I do half the Vert. Instead of 300 joules of Vert, I do 150 joules of Vert. Okay? So, half the distance, half the voltage. What I'm getting here is that the electric field times the distance is my voltage, N. Electric field is the E, D is the distance, N. Let me show you that. If I start with a charge, and this doesn't have to be a plus 1 coulomb, just any positive charge at A, and I push it slowly to B. Well, the grand high Vert energy equation is what it always is. If I start from rest at A and move it slowly to B and stop, the change in kinetic energy is 0. And now I replace my electric potential energy with the test charge times the voltage, times the rate. And that voltage is what I'm looking for a formula for. Well, how much Vert do I have to do as the external agent? Well, my force times the distance is the Vert. That's our operational definition. Well, how hard do I have to push? What is that force by the hand? Well, if I look at a free body diagram, I have an electric force, and that's given by this definition of the electric field. It's just a test charge times the electric field. Now if I want to push this at a slow, constant velocity, I got to fight that force, that electric force. I have to push just as hard. I have to push a little bit harder to get it started, a little bit less to get it stopped, but on average I got to push just this hard with the hand. And I'm pushing in the same direction that it's going, positive air. Now I put that in, and here is the magic. The Q's cancel. And what I'm left with is a formula for the voltage that is so simple. The voltage between A and B is equal to the electric field times the distance between A and B. Okay?
You're getting it right from the horse's mouth.
Yes, you are. Horses patooed. Okay. This equation is so simple that it's dangerous. It's dangerous because you are going to want to use it for every single problem on the midterm. And there is great big yellow caution tape around this equation. You can only use this equation in regions where the electric field is uniform. What that means is that I have to have field lines that are everywhere parallel. Well, where do I have that? Between plates, between positive and negative plates, or in the vicinity of a single charge plate. Those are the only types of problems where you could use this equation. Don't be trying to use it with point charges. You'll get garbage. Okay? Garbage. Okay. Now, I have this battery, and the battery is 12 volts, and it's connected to capacitor plates, just parallel plates, metal plates, that I can put close together or pull far apart. And the question is, how am I affecting the field, the electric field between the plates, as I change that distance? Well, first of all, we have to recognize that the job of the battery is to keep these plates 12 volts apart. Okay? What that means is the battery, come hook or by crook, is going to make it so that I have to do 12 joules of air to get a +1 coulomb from this plate to that plate. Okay, that's what the battery does. In your tutorial, you will see why that is true. The tutorial that you're taking today and tomorrow and Wednesday morning. Now, a quick word about the tutorial. As I promised, it's 6 pages long. You've done the first 2 pages in lecture. You can zip right through those really quick. The 4 pages that are left, however, are not trivial. Unless you happen to be reading in chapter 17. And you happen to read examples 4 and 5. Because you'll find that examples 4 and 5 are the tutorial. And you're going to find that examples 4 and 5 are almost identical to the tutorial homework. The tutorial homework, it turns out, is only 1 page front and back. So there is that. Now, if I ask you what is the electric field between the plates, you can find that with the equation. But just an aside, that's not what I'm going to ask you on the exam. I would never ask that. What I would ask is, what's the electric field halfway between the 2 plates? Or, what's the electric field 1 millimeter from the negative plate? Or, what's the electric field 2 millimeters from the positive plate? That's what I'll ask. And that's evil. Why is it evil?
Because distance doesn't matter.
Because the distance doesn't matter. It doesn't matter where you are between those plates. My electric field is going to be the same at all of those locations. And it's going to be given by the equation. If I solve this equation for E by dividing both sides by D, I just get the voltage, which is 12 volts, divided by the distance between the plates, which is 1 centimeter, 0.01 meter, and I get 1,200 newtons for each coulomb. Now wait a minute, Greg. Let's look at your units here. If I use that ED equation, it tells me that the electric field is going to be the change in voltage from A to B divided by the distance from A to B. Well, that's going to be 12 volts over 0.1 meters, no, 0.01 meter, and that gives me 1,200 volts per meter. And yet you wrote it as newtons for each coulomb. How do you get away with that? Well, remember what a volt is. A volt is a way of honoring a dead professor. Okay? It really means joule for each coulomb. And then I've got to divide by the meter that's there. And a joule is just, well, that's a unit that we named to honor a dead physics professor. But really, it's just a Newton times a meter. And we got to divide by what's in the basement. And now you see that the meters cancel, and whether I do it in volts per meter or newtons for each coulomb, it's all the same. It's all the same. Now, if I have two regions, region 1 and region 2, and I were to ask you, what direction does the electric field point in region 1? Well, you would say from high voltage to low voltage, because it always points from high voltage to low voltage. If I asked you what direction does it point in region 2, you'd give me the same answer. But here's the more interesting question. In which region is the electric field stronger, region 1 or region 2? Talk to your neighbor. In which region is the electric field stronger?
Now what's the difference?
The top one.
I think it's still not because it's bigger. The difference in voltage.
Well,
Okay.
oh no, it's this divided by this distance.
In the interest of time, let's answer this together. If I look at two locations, A and B, the distance between A and B is going to be the same in region 1 as it is in region 2. That's the distance here. So what I want to look at is, in which region do I have a bigger change in voltage? Okay? And if I look in region 1, I'm going from 140 volts to 180 volts. That's a change of 60 volts. If I look at region 2, I'm going from 340 volts to 420 volts. That is a change of 120? 180.
No, just 80.
420 minus 340.
Ah, so I had 40 up there. No, I'm going to B. I'm going over to here. My bad. So up there I have 100 and
Oh,
up there I have 60. Here I have 120. You're dismissed.
is it region 2?